I'm thrilled to announce our first keynote speaker of today, Veysel, who is the head of data science here at John Snow Labs. Veysel will speak about the important topic of automated bias, robustness, and data quality testing for NLP models. Thank you for joining us. Take it away, Veysel.
Hello, everyone. This is Veysel from John Snow Labs. I am leading the healthcare data science team at John Snow Labs. And today in this keynote, I'm trying to cover our team's latest effort towards automated bias, robustness, and data quality testing for NLP models, which would be quite handy given that our job is to ship all these state-of-the-art models in the healthcare domain, right? So let's start with what we are trying to achieve here. So when we are talking about NLP, actually any machine learning model, we always talk about the accuracy, right? So as long as we have a nice and decent accuracy on a held out test set, we always say, okay, we are good to go, so we can just ship this model and then start using it right away. But the reality is not like this. So because classic classic machine learning benchmarks do not say anything about where the model is failing. Of course, there are some explainability tools that is explaining that is giving some clues, but when it comes to how to fix it, we usually have no clue at all, right? So, and the most important thing is we usually miss the fact that held out test sets, even if we don't touch it, we don't see it, there's no data leakage, let's say, even in an ideal condition, held out data sets usually contain the same biases as the training data, because we usually have one giant data set, right? Like one decent data set, and then we split into test, training, and validation. So the biases in the original data set goes to the test set as well. So it's inevitable, and then we may never notice if this model is going to fail in the future, because even the held out test set is not enough, as the data set distribution may change in the future, and then adapting the existing model to a new domain, new data set should be possible without annotation, but which is usually not the case, right? Because you usually end up in a situation that you need to annotate tons of new data to cover the weaknesses of your model tells you after the test. So that's why we kind of need to find a way to detect these biases, these weaknesses, and then fix it before shipping the model. Like during our model iteration, we need to find this. So latest research says that estimates that average 3 to 4% of errors are detected in even the benchmark data set that we are using in academia. So in the last few years, there are two nice research towards this goal. The first one is Checklist. Checklist is all about model testing using perturbations, which is published like 2 years ago. It's a nice paper that is kind of adding some perturbation to your to the test set, to any data set, and then checking your model against these perturbations. For example, like one assumption is that given a sentiment model, changing one entity in that phrase shouldn't change the sentiment classification of the model. For example, Chicago to Dallas shouldn't change this review from positive to neutral, right? And then the same for Brazil to Turkey. So which means that if we can apply certain perturbations to our test set and then check our run our models again, we can kind of find the weaknesses against or vulnerabilities against all these perturbations using this technique. Then clean lab, because checklist has nothing to do with fixing the errors. It just reports, but there's no way to fix it. And then clean lab looks at the things from another perspective, and then it claims to detect the label errors. It's not just NLP, they also work with the computer vision, by the way. So they are using confident learning and then and some other techniques to detect the label errors, because most of the time you may not even notice the error from the model comes from the labeling error, because we usually have multiple annotators annotating the same data sets, and then even if they are coming from the same domain, let's say that two physicians annotating two different notes, they may not agree on the entities that they annotate, because they are all their brain is crafted from the experiences that they have developed so far, right? So that's why the more they annotate, let's say that we assign a annotator to annotate thousands of documents in a week or in a month, and then it's inevitable that the human will start make some errors, let alone the inter-annotator disagreements, right? So CleanLab tries to find this error, and then so that you fix them before it also offers some solutions to fix, by the way, before you start training. So what we did here is that we try to merge the two of them and then adding some other techniques and methods from our own experience. So for example, since Spark NLP for Healthcare Library and Spark NLP open source library is developed by Johnson Labs and with our team. So, and then working with hundreds of different customer facing projects, we developed some techniques to attack these issues, right? Because we have more than 5,000 pre-trained models. Just in healthcare, we have 700 pre-trained NLP models that all these customers are using on a daily basis in industry right now. So which means that we get tons of feedbacks and critiques and some suggestions, and then we try to improve all these models. So we need to make sure that the models that we ship as a pre-train should work out of the box. So we developed these techniques and then added some other modules under our Spark NLP for Healthcare library. So we call it model testing module. Right now, it's going to be shipped into Spark NLP for Healthcare library, and then later we plan to outsource this. So we have 5 modules under model testing models. The first one is robustness via perturbation. So robustness via perturbation is basically testing the ability of a model to keep similar level of accuracy under certain perturbations, right? So because the assumption is that the model should assign the same label even after applying that certain perturbation. So you don't need a label test set to do this, because you can just pick one text data set and then apply all these perturbations. We devised more than 10 different perturbations, by the way, which I'm going to explain. And then we get a prediction, and then we apply the perturbations and then get another prediction. So we regard one of them as a ground truth and then try to see how consistent the model is. It doesn't matter how true it is, because we try to make it possible without labels, without annotated data as well. You can use annotated data as well to do this, which under that case, if you are using your annotated data to see these vulnerabilities, you will get more detailed feedback after you run this module. The second one is fixing this weaknesses that we detect through robustness text. So since we see that, if we talk about name identity recognition model, let's say that we run the robustness test and then we find some entities are vulnerable to certain perturbations. So rather than applying the same perturbation in a reverse way, we apply the perturbations in a smart way that is only applicable to those entities, because without knowing, you may hurt the entire model learning mechanism while trying to fix one issue, because these are deep learning models, right? Like we are talking about. So while trying to fix this, you may end up in a situation that you may corrupt the other issue. You may create new issues in the other entities. So we apply some adaptive augmentation, which I'm going to explain as well, and then some reverse perturbations to fix this issue and end up with a brand new training data set. The third one is noise label detection. It is just like CleanUp does. It's trying to find the annotation errors. But we are using different techniques to find these label errors, not just confidence learning. We are using tons of other techniques, which I'm going to explain if I have a time. And then detect assign some scores for each label, and then try to fix via automated fashion in the next module. So we kind of resolve the potential labeling issues in an automated fashion. This automated, you can do this in one click, one line. You can also customize this further if you know what you are doing. You can even assign different probabilities to different entities and different perturbation tests so that you can control your augmentation as well. Or you can just let it go in one single click so that it's going to be fixed according to the test that we run to find those errors. And then the last one, both checklist and cleanup doesn't have it, by the way, bias detection. We run some gender or age or ethnicity detection classifier models under the hood to find to assign gender and age and ethnicity, or it could be applied to many other metadata, by the way. So any other to find underrepresented population or underrepresented subcohort of the same data set, we run certain classifiers under the hood and then assign labels. Again, you don't need a test set annotations for this. And then we try to find how the model perform for each subcohort. So we call it bias detection. So these are the sample codes that we apply to run all these modules, right? It's we designed in a way that you can just import from the internal library, Spark for Healthcare library, and then run one line of code to run the robustness, for example, or fixing the robustness, or finding the noise labels. So all you need to do is feeding an NER pipeline, which you can build in Spark NLP, because you can pick any NER model, any assertion, any classifier over there. Later on, we are going to make it compatible with the other NLP libraries as well, but for now, it only works with Spark NLP pipelines. So, and then you can also fit labeled data or unannotated data set, like with no labeled, right? So, and then you will be able to end up with a fixed labels or label errors in a nice PDF, or some test results that you can save as a JSON and then share with your colleague. So if you compare Spark NLP testing model with checklist and cleanup, as you know, checklist is all about robustness via perturbations, and cleanup is all about noise label detection. None of them offers the other solutions, like how to fix the perturbations. Of course, if we tweak it a little bit, checklist can also be used for this, but you need to spend some time to do this, which may not be a trivial job. And then the cleanup doesn't do any perturbation; it just looks at the table and then try to find the label errors and then fix them on the fly. But it's not doing bias detection or perturbation. But Spark NLP right now can do all of this. And in NER assertion, relation extension, all the NLP tests that we have right now supporting under Spark NLP for Healthcare library. So if we talk about the first perturbation, these are some of the perturbations that we devised so far. So we have more than 10 different perturbations we applied. So for example, the first one is introduce typos. So given this sentence, we introduce some typos to randomly with some probability that we define, by the way, and then we have a new sentence. So next time we test this sentence with our models and then see if the model is still able to detect these entities, let's say, if this is an NER. Or replaced by synonyms, this is basically finding the entities and then try to replace those entities with its closest and then with its synonyms, and then try to see if the model is looking at certain things in a sentence rather than the whole generalizable aspects of a model, right? For example, if you change one entity with another word from like a synonym list, the model shouldn't diverge more, right? Shouldn't diverge and then shouldn't assign another label if that entity is drug, let's say. So, and then we have replaced by same entity, modify capitalization error. So we have some simple perturbation and complex perturbations as well. So we tested this with some NER clinical model that we have, like NER_clinical. So we tested our intuition. My personal intuition at first was that BERT-based models would be more robust against these perturbations, but looks like it is not the case. So they are, like LSTM versus and BERT-based models, name identity recognition models, both vulnerable to this kind of even the simple uppercase perturbation. As you can see, they are almost same against these perturbations. And this is the summary of selected perturbations for the same model. So we applied 9 perturbations, simple ones, and then ended up with a situation that we somehow even see 40% F1 score, which means that the model failed 60% of the time when we applied this perturbation in the second round. So we replaced random sentences with some lowercase sentences, and then looks like model is highly vulnerable for this specific model, is highly vulnerable to lowercase. So then if you find these errors, now we can try to fix this, right? So fixing is also one-liner. So we have two ways of fixing this. The first one is perturbation augmentation in a way that we detect through robustness tests, because each entity will be impacted at different level for against certain perturbation. So we have a one-liner fix all of them. We do some calculation and then try to fix the most problematic entities, or you can control one by one. And another one is synonym augmentation. We are using Spark NLP for healthcare resolution models, entity resolution models, because we know that there are some synonyms or similar disease names. If I use ICD-10 codes, right? If I use CPT code, I can find a synonym for the for procedures. And if I do the same for ICD, I can find some synonym or similar, or another drug brand name rather than a commodity. We can use Jantovan, etc. So that you can do this in one line. You can just set this synonym augmentation true, and then it's going to be like the pipeline will find the entities and replace them according to these resolvers. So we applied this on the same NER clinical model, and then tested on the same test set, like unseen test set. At first, after the initial robustness, we saw that we ended up with these F1 scores, but after applying these fixing techniques that I just explained, like synonym and perturbations, we tested on the test sets. We trained the model again. We tested on the same test set again, and then we ended up with 16% jump in the problem entities, and test entity improved 15%, and treatment entity improved 23%, which means that we get a nice boost even after applying some basic fix or some augmentation fix. So let's talk about noise label detection. Noise label detection, we are, as I said, CleanLab does this with the confidence learning, but we devised other solutions, as you can see on the left-hand side, like even the average length of chunks or the chunk frequencies, or using some zero-shot NER approximation that we developed lately, or comparing the entities with some random question answering language models. We created a one single score, error score, that is going to assign to each ground truth label. Let's say this is an NER model, so we want to find the problematic labels that are assigned by human annotators. And then, as you can see in this example, dots are labeled as a problem entity, which they shouldn't be, right? So this should be detected by the noise label detection. Then if you want to fix this on the fly, so there will be some like error score assigned to each one of the ground truth. The higher the score, the problematic the label. So which means that this is almost one. So this is a problematic label, and this is the same as well. So this one looks good. So you can set some threshold and then fix all of them on the fly as well. If or you can just apply some micro level adjustments in the parameters and then fix some under some supervision. Then the last module is bias detection. So the bias in the data side might come from different resources, right? It might come from the data. It might come from the real world patterns, which is usually the case, because in real world, not all the populations are equally distributed or represented, as you know. So there are some application injustice or some regulatory injustices as well that might cause some bias. And then the last one is, when you have a bias in your data, you have some, your models are also biased as well. So if you don't fix the bias in your data set, you will end up in a situation that would be hard to fix after you ship the model. So we developed some classifiers, document level classifiers, to detect social determinant of health or demographic characteristic of a patient that specific clinical note talks about. So you can apply this. This is not just for healthcare, by the way. You can apply this for any other domain, legal, finance, or sport, or some politics, right? So we devise some classifiers to detect the gender, assign gender to each note, or finding the age of a patient that is being mentioned in the note, or ethnicity of the patient. When we do this, like we tested on the same NER data set that we have, by the way, problem test treatment entities, which we call it NER clinical. As you see, almost like the female population, like surprisingly, driving the entire data set right now. It is 3 times more than the male population. So I would expect some bias against male population in this data set. But when we did this, when we test this, like as you can see, female and male, like the first 3 rows is the female metrics, like female population metrics, and then the second one is male population, and then the last one is unknown, which the classifier couldn't find the gender at all. So as you can see, the F1 scores, the accuracies are almost same, so which means that this model is not biased against gender. So you can do this for the for any other domain, as I mentioned, and then you can run age classifier or ethnicity. By the way, you don't need to run this if you are using this model, because we already run this under the hood. We have different version of classifiers, so you would be able to detect the bias before you start training your model. So I hope you enjoyed. You can ask any question. I will be here to answer your questions. I hope you enjoy the rest of the sessions in NLP Summit. Thank you.